we can also use LTSpice to simulate these convolution problems. I have to come up with a circuit that has an impulse response equal to the given impulse response. And in that same problem 2.4-7, the impulse response was e to the minus t u of t. A circuit that has that impulse response is just a simple resistor in series with a capacitor, a 1 ohm resistor and a 1 farad capacitor. The input is a voltage source and the output is the voltage across the capacitor. That problem had 4 parts. In the first part, we applied a unit step. In the second part, we applied an e to the minus t u of t. In the third part, it was an e to the minus 2t. You'll notice here the 0.5. In LTSpice, actually, to specify an exponential, you input the time constant. So that's t over tau. So t over the 0.5 would give me the minus 2t that's specified in the problem. And then finally, in the last part of the problem, the input was a sinusoid with a frequency of 3 radians per second. In LTSpice, I have to specify the frequency in hertz, so I just take the 3 and divide by 2 pi to do that conversion. And when we run the simulation, I've labeled the output voltage across the capacitor for the 4 different parts, YA, YB, YC, and YD. And so in the results, I plot those 4 voltages, and I compare that to actually the theoretical results that I got by analysis. Actually, in this particular case, I add a little bit of an offset to our theoretical results so that you can see both graphs. If I don't do that, they overlap, and it's hard to tell that there are actually two separate plots in each of these figures. But again, doing this, comparing my LTSpice simulation results to my theoretical results, this gives me a lot of confidence that I've done the theory right. I'm getting really good agreement between my simulation results and my analytical results.